All right, let's step through one of the problems that we had in class today. It was a little bit rough. Apologize for that. I'm still. It's been a long week. Let's just put it that way. We've all been there, right? Okay, so 3.34 out of the book is what we're talking about, where we have a 100 test specimen with breaking strengths, normally distributed, 1% significance, 67.45 KSI for a mean, and a standard deviation of 2.92 KSI. So we talked in depth about why we would choose either side of the bounds here for our buckets, and we decided that the more conservative would be to report to our reader the low end of the breaking strength. That way, if they designed for those breaking strengths and they happen to get one that was on the low end of that, they'd still be safe. Okay, so now we have the observed frequencies here, which means we have our number of samples is 100. Our buckets, we have 5 buckets here. And so because we're using sample mean and sample standard deviation and we're choosing from buckets or bins, then that means we're going to remove 3 degrees of freedom. So our nu is going to be equal to 2. Our mean and standard deviation are given to us. And this is where I went a little off the tracks during class, is we are going to use the z-table because we do have these values here. And so out of the z-table, that is going to give us the probability. And that is going to be our expected frequency or our expected value that we would know based off of the Gaussian distribution. So that's the part where we could either use the z-table or we could use the equation. And there's 2 different ways that we could go about that, and that's where it was getting a little bit muddy. Again, I apologize for that. Thanks for being patient with me. So our bin bounds are going to be on the low end, 59. We're going to go all the way up here, and then we're going to have to get the upper side of this top bin. So that's why we've added the 74.5 here, is because that's the upper side of the top bin. So then we use the z-table to calculate out what the expected values are going to be. So we have our bin bound, which is 59, minus our mean of 67.45, and we end up with these values here for those z-bin bounds. And then since we're using the z-table here to calculate out what our expected number is, we're going to have to use half of the table. And so we're going to take that half and we're going to subtract off the value to look up what our expected number is there. So now we can use these expected values in our observed minus the expected equation. And so that's what we're running through here is going, we've got the observation, number of observed frequency right here. And then we have our expected, which is our bound from the top side minus the bound of the bottom side of those, and we calculate out, times the number of samples that we have, and we get these frequencies in here. So this is where our expected values are going to be. So we throw those into this equation here. We go through our observed, which we are given, minus our expected, which is what we calculated out right here using the z-table. And then we get our chi-squared of experimental squared. Okay, so that's 0.83. We put that on our plot over here, and obviously this is straight from the slides, and this is not the right number, but it's 0.83 if we put the 0.83 over here. And then our significance is 0.01. We looked that up in the table based off of a nu of 2, because we had 5 buckets minus 3, so a nu is 2. And our chi-squared, our significance is 0.01, so out of the table we get 9.21. And so if we have our expected, oh man, I keep saying that wrong. Our experimental chi-squared is way down here, 0.832, and our table is 9.21, so it's way up here. So we're definitely on the do not reject. And so the actual distribution cannot be said to be significantly different from a normal distribution at a 1% significance. So that means this is a pretty good fit as a Gaussian distribution. Hopefully that helps. Maybe run through this video a couple times.